In this lecture, we will talk about the impulse response. Remember that in one of our previous lectures, we already talked about step response, and what step response was. It was that you, given an LTI circuit, you set all initial conditions to 0, and from the input, assuming that you have a single input, from the input, you apply unit step waveform, okay, and then you go to the output and check response, and whatever you see is what we call step response. And by output, we mean any variable of interest. It could be capacitor voltage, or it could be some resistor current. Okay. Now, the impulse response is defined in the same fashion, the only difference being that from the input, you apply unit impulse waveform. Okay. One nice thing about impulse response is that if you know the impulse response of a circuit, then you can figure out the response to an arbitrary input. Okay? And therefore, in a sense, the impulse response contains all the information, or it's a complete characterization of the circuit from the input-output point of view. Also, we will see in 202, not in 201, that it's very close, the impulse response is very close related to the concept of the transfer function. Okay. Therefore, it's worthwhile to spend some time on impulse response. Before we start our analysis, let's remember some of the preliminaries that will be required for our analysis. In particular, let's remember about time invariance and homogeneity. Okay. The zero state response. Okay. The circuit is time invariant, or by time invariant circuit, we mean the following. You make an experiment in the lab with your time invariant circuit on Tuesday, and you go ahead and make the same experiment on Friday, and the results of those two experiments match one another. Okay, so that's a very simple definition. In mathematical terms, it boils down to the following. Okay, so let's this box represents an LTI circuit with zero initial conditions. Okay, so you set all the capacitor voltage to 0 and all the initial inductor currents to 0. Okay, so that's what we mean by definition by zero state. And then you, from the input, you apply some signal, that's called W of t. Okay? And our inputs in our circuits are either voltages by an independent voltage source or currents from the independent current sources. For simplicity, suppose that we have a single input. Okay? And then you go to your output, some capacitor voltage or inductor current or something else, any branch current or voltage. Okay? And that output we denote by y of t. Okay. Now, since the circuit is LTI, that is time invariant, this is what's going to happen if you excite the same circuit, again starting from zero initial conditions, with the same input but some other time. Okay. Same circuit with zero initial conditions. Then you get the same output. Okay? So what that means is V of Wt minus T0 produces Y T minus T0. Okay? So let's try to visualize what that says on this simple example. Time invariance. So here we have, let's say, this pulse t, w1 of t. Okay. So this input is given to, is applied to our LTI circuit, and the circuit is at rest. Okay, initially, so 0 initial condition is what we're assuming, and what we see at the output, suppose, is the following waveform. Okay, so since everything is 0, the signals, initial conditions before t equals 0, therefore in our curves this part is always at 0. And at the output, suppose we see something like this. Something like that. Now the question is, for the same circuit, suppose we apply the following input. T, and let's call that input W2. Same circuit. Again, 0 initial conditions. And the input that we're applying in the second experiment is this. That's 3. The question is, what will we see at the output for this particular input? Okay. Now, by using time invariance and also homogeneity, we can easily construct y2t from y1 of t information. Okay. So this output is y1 with output corresponding to input w1. So let's do that. Let's use time invariance and homogeneity and figure out what y2 of t would look like. Okay. So let's decompose w2 of t into, or write it as sum of 2 separate waveforms. Okay. Plus t0, 0, t. First we call w3 of t, the other one we're calling w4 of t. w3 of t is this part, and w4 of t is this part. Okay, so we write w2 as sum of this piece plus that piece. Okay, so we have 1 for w3 of t. Now that is same as w1 of t, and for w4 of t we have again a pulse, but it's shifted in time and also it's scaled by a factor of 3. So w4 of t is this. 1, 2, and the height is 3. Okay, so that's how we can write W2 of t. And now, since the circuit is LTI, we can apply superposition, okay, using homogeneity and time invariance. Now, this produces the output, which we're calling Y3 of t. Okay, and this output is no other than Y1 of t, because W3 of t is W1 of t. Okay, so we have, therefore, this 1, 2. Okay, so that's our W3 of t. And how about this guy? T0. Now, since W4 is shifted version of W1, okay, 1 units, and also it's scaled version of W1 with a factor of 3. To figure out the output, all we have to do is just shift this output 1 unit to the right and scale it by a factor of 3, which we can do because the circuit is LTI. And if you do that, this is what we have. So nothing happens until t equals 1, because nothing happens until t equals 1 with the input. So everything is set to 0, and also initial conditions are set to 0. And then we apply, and W4 is constant at 3 for a while, and then it drops to 0 back at the second. So what happens is we have this shape, but scaled with a factor of 3. So it's something like this. This is 2, and this is 3 times 2, 6. And let's call this Y4 of t. Okay. And then, since W2 of t is W3 of t plus W4, and we can apply superposition and say that Y2 of t must equal Y3 of t plus Y4 of t. By superposition, we can write Y2 of t equals Y3 of t plus Y4 of t. T, this is Y2 of t. So we have 6. This is 0. So we have Y3 of t. Then it decays towards 0. And this is t equals 1. And then we have Y4 of t. It looks like this. Decays from t equals 2 onwards. Something like that. And now what we're going to do is we're going to combine two. We're going to sum Y3 and Y4. So the overall waveform would be, okay, so this is Y3, and this is Y4. The overall waveform is, well, until t equals 1, Y4 4 is 0, therefore that's part of y2. And then from 1 onwards, both y3 and y4 are active. So what we're going to do is we're going to sum those two things, okay, those two curves, and the sum will look something like this. Okay, it will be slightly over 6 when we reach t equals 2, because y4 is 6 and y3 is something tiny at that point. And then we decay. So that would be y2 of t. Now, since it's not easy to visualize impulse response, now we're ready to talk about impulse response, or begin to talk about impulse response. Since it's not easy to visualize that much unit impulse function, therefore we will try to see it as the limiting waveform of a pulse. Okay? So let's obtain the pulse response. Then from pulse response we will try to reach the impulse response. Pulse response. Let's deal with the following circuit. Plus minus S of t, R, C, and this is our output variable of interest. VC 0 equals 0. So the question is find VCT for the following input. Okay. 0, it's constant, it's some value for a while, and it drops back to 0 at some time. And then from that point on, it's 0. This is t, and this is Vs of t. Okay. Now, we already know the step response, okay, and we can write Vs of t as sum of 2 steps. Note that Vs of t can be written as a step with magnitude V0 and a delayed step with the same magnitude but opposite sign. Ut minus capital T. Therefore, take the step response, multiply by V0, and that's the first piece of the output, and then you do the same thing for the other guy and sum those two separate outputs, and the overall result would be the pulse response for this waveform. Okay. Now, since the initial condition is 0, okay, we are talking about a zero state response, we can apply superposition. So, response U2 V1 of t is okay, so response U2 V0 U of t, okay, for that piece. Let's call it V1 of t, the first piece of the solution, and it's V0 1 minus e to the minus t over the time constant ut. Okay, it starts from 0 because at t equals 0, 1 minus 1 is 0. And what happens is it converges with the time constant of RC, it converges to the constant value of V0. Okay, so that's the step response. for a step, well, that's the response for a step function with magnitude V0. And now response due to the other piece is t minus capital T. Let's call it V2 of t. And that's minus V0, 1 minus E t minus capital T over RC t minus capital. So this is basically, you take V1, okay, slide it capital T units to the right, and then you flip it over the horizontal axis. Okay, and that we can do thanks to the fact that this circuit is LTI. And then we see T response, pulse response, is the sum of V1 of t and V2. And therefore, Vc of t equals V1 of t plus V2 of t. So that will give us something like this. Now, V1 of t is this. Start from 0 and it's converted to V0 with time constant RC. And V2 of t has the same shape, but it's upside down. And this is t. So that's, so this is V1 of t, and this is V2 of t. Then if you sum those two waveforms, what you obtain is the following. Okay. So everything will be just like V1 until t equals capital T, because V2 is 0 at that point, or V2 is sleeping. And then from that point on, from capital T onwards, V2 of t starts pulling things down, and in the limit, this is taking us V0 units up, this is taking us V0 units down. Therefore, they will be balancing one another, and the overall response will converge to 0. So here, from here we're going to be converging to 0. So the overall response will be this dark curve. This is Vc of t. Okay. Now, to obtain the impulse response, what we're going to do is we're going to consider a pulse, okay, of this form. Well, since we have to apply unit impulse, and we want this guy to converge to unit impulse function in the limit, this area must be 1. Okay, so V0 times capital T must be 1. So what we're going to do is we're going to pick V0 to equal 1 over t, let's say. And then what we're going to do is we're going to obtain this curve and try to see what happens to that curve, the response, as you squeeze further and further this capital T. Since the area must remain 1 at constant, as you squeeze this interval, as you squeeze this capital T, the height must increase so that the area is kept constant. And then in the limit, the pulse response will give us the impulse response. Okay. But even before that, let's do it in a more mathematical or less visual way using the differential equation. And then once we do it the visual way, we can compare the two answers. Hopefully they will be the same. Okay. So now let's talk about the impulse response. So by definition, it means zero stage response unit impulse function. For unit impulse delta t input. Now let's consider the same circuit. This is where we apply the input from, and now Vs of t is unit impulse function. So let me redraw the circuit. Plus minus. Now we're applying delta t from the input, and the initial condition is 0. So we have to now introduce this notation of 0 minus, because 0 minus and 0 plus will be different. Here we didn't need to bother with that notation. Okay, because this is a bounded then here we have R, and this is the capacitance. Now we're looking for Vc. Okay. Now Vc, the solution, Vct, is what we're going to be calling impulse response for this circuit, where the output is the capacitor voltage. Now, let's try to figure out the answer using the differential equation. And then, in our second approach, we're going to go more visual and treat the impulse function as a pulse in limit, that is, this capital T is becoming smaller and smaller, and V0, which is 1 over T, becomes larger and larger. And then we can compare the two answers. Okay. Now, what's the differential equation? Okay. This voltage must equal plus minus this voltage plus minus that voltage. Okay. And this voltage is IC, the capacitor current, times R, and capacitor current is CdVc. Therefore, R IC plus VC, that's RC dVc plus VC. Therefore, dVc plus 1 over RC VC equals 1 over RC delta T. So that's the differential equation describing the evolution of Vct for the input delta T. Let's call it equation 1. Now, in this case, the case that we're considering, that is initial condition 0 and input is unit impulse function. The solution Vct to the differential equation that we just obtained, equation 1, is called impulse response for this circuit. Okay. And the impulse response is usually denoted by H. H of T. Okay, now we will try to figure out H of T. So let's consider one. Okay, consider differential equation 1. Okay, so we have everything we need to be able to talk about it or figure out the solution. We have the differential equation and we have the initial condition. Now, due to the impulsive function, okay, the impulsive input function VC0 plus may not equal VC0 minus. Okay? Because this impulsive input may create some impulsive currents, and whenever the current passing through capacitor is impulsive, then we should expect jumps, okay, in the capacitor voltage. Okay, so since we know VC0 minus, but we don't know whether VC0 plus will be equal to VC0 minus or not, okay? And we expect jumps because we have an impulsive input, okay, in the picture. Therefore, let V0 denote the new voltage that the capacitor will experience after impulse produces its effect. Okay. So if that's the case, if V0 is what the 0 plus value of the voltage, and then it's starting from 0 plus onwards, this source, since its impulse is 0, therefore we can replace the short circuit and the situation becomes homogeneous, okay, with high input. And for that we can easily write down the solution. This is the initial condition, okay. By initial condition we mean VC0 plus times e to the minus t over time constant. Okay. Then for t positive, VCT equals V0 e to the minus t over RC. Okay. Also, for t negative, again, this thing is 0, initial condition is 0, everything is 0, therefore VCT is also 0. VCT equals 0. Okay, so this is a piecewise definition of VCT. Note that using the step function, you can combine that piecewise representation to just a single equality representation. Okay, you can say that VCT equals this guy times the unit step function, which is quite a convenience. Hence, we can write VCT equals V0 e to the minus t over RC u of t. Now that this single equation tells what both of these equations are telling us. Therefore, it simplifies a little bit our lives. Now, we know this form of the solution. All we have to figure out is this V0. That's the one we have. And for that, what we're going to do is we're going to use the differential equation. That's the only thing that we can use. Question. What's V0? Or what's VC0 plus? Voltage that capacitor jumps to from 0. So one way to find the answer is place VCT equals V0 e to the minus t over RC t. So put your candidate into the differential equation and see what you get. Equation 1. So let's do that. This yields the following: d over dt, V0 to the minus t over rc ut. So differential equation was dbc plus 1 over rc bc equals 1 over rc times delta t. Okay, dbc plus 1 over rc bc equals 1 over rc delta t. Okay, now let's differentiate this and then perform some calculations, if there will be any, and then see what we get from there. Okay, now let's differentiate that. What we have is, note that here we have product of two functions, therefore by chain rule, derivative is this dot times ut and this times ut dot. So this derivative of that is minus v0 over rc minus t over rc ut plus v0 e to the minus t over rc times this dot, okay, and by, we know that, we said that the derivative of step is impulse. Okay, so under differentiation, u of t becomes plus v0 over rc e to the minus t over rc ut, and that equals right hand side. Okay, first observe that this cancels with this. Okay. So what remains is some function multiplying impulse equals some constant multiplying impulse. Okay, so for an arbitrary function, that would tell us that the equation will not be satisfied. But we're not dealing with an arbitrary function. We're dealing with a very special function, and let's see what that implies. First of all, using the sifting property. Okay, now that delta multiplies the continuous function. Therefore, this thing we can replace by a constant, which is the value of this continuous function at time t, which makes the argument of our impulse 0. In this case, it's t equals 0. Okay, we obtain that constant times delta t. We can, for all practical purposes, we can replace this expression with that. Hence, this equals v0 e to the minus t over rc. This function evaluated at the point which makes the argument of impulse 0 times impulse. Okay, so that should equal 1 over rc delta t. And this at t equals 0 is simply, okay, v0 times delta t, and that equals 1 over rc delta t. And that tells us what v0 should be. Therefore, v0 must be 1 over rc. Therefore, the impulse response, which we obtain directly from the differential equation, is h of t 1 over rc e to the minus t over rc times step